Hello everybody, and welcome back to another video of Edmund's Maths. So, today we're going to be looking at the incomplete beta function again, and we're going to try and sketch it. Now, as you recall from last time, the incomplete beta function looks as follows. Beta n m of x is defined to be the integral from t equals 0 to x dt t to the n minus 1 times 1 minus t to the m minus 1. Okay, so the thing is, obviously for some kind of general n and m, you can't really sketch the function. I mean, effectively this is a function of three variables, n, m and x. However, we will only be treating it as a function of x because we're effectively treating n and m as constants. But what can those constants be? Well, we are going to be specifically looking at the case of n is equal to a half and m is equal to 3 over 2. So if you plug these into the function, you get n minus 1. Well, n is a half, so n minus 1 is minus a half. And you get inside the integrand, you get 1 minus t to the 3 over 2 minus a half, which is a half. So our incomplete beta function now looks like this. And indeed, it is a function of one variable now. But how the hell are we going to sketch it? Huh? I mean, the x is up there. Christ, well, I think one good approach is to actually look at the function inside the integral. So we're going to actually be examining this function. Let's call it g of t. And then we will sketch this function and then just look at this function as the area beneath this function. And then we can successfully sketch it. But how are we going to sketch this? I mean, this is also a beast. So, you know, we're going to have to pay some careful attention to sketching this function. All right, so I think the easiest thing to do for now is to rewrite this function as uh, 1 over t minus 1 to the power of a half. And there are two things you can immediately notice from this. The first thing I want to say is that we only really care about x going between 0 and 1 in our incomplete beta function, so therefore we only really care about t going between 0 and 1 in here, which is a very fortunate thing, because if t was any greater than 1, then we'd have a negative inside here, we'd have therefore a complex number being g, and we're just defining this for real variables in our problem, so that's good. So the first thing you can notice from this is that when t tends to 0, so g of t tending towards 0 from the positive direction is tending towards infinity, because essentially this term becomes large, it dominates the other term, blows up. We can also note that when g is 0, then we must have t equal to 1. So we've got two very important points. We've got 2 points where we know that the function crosses the axes. And remember, this is still for g. We're not talking about the incomplete beta function yet. That boy is going to wait a little while. What can we do next? Well, we've already got an asymptote. We know where it crosses the x-axis. It doesn't quite touch the y-axis. It just kind of asymptotes towards it. But what other things can we look at when we're trying to sketch a function? Well, of course, we need to look at the derivatives, look at the turning points of this bad boy. So g prime of t is equal to, well, that's going to give you, by the chain rule, minus 1 over t squared times a half times 1 over t minus 1 to the minus a half. And forcing that equal to 0 at turning points, well, this doesn't give us any solutions with t in our domain. And of course, our domain of t, as we've already agreed, is t is in this domain. Now, within this domain, this function can't possibly be equal to 0. So therefore, we know that there are no turning points within the region of interest of this function. Well, what now then? I mean, are there any interesting points? Are there anything interesting about this function that we can continue to look at? Let's just have a little look at how it might look like, what the function might look like. So, if this is g and this is t, we know that it's 0, t equals 1, so we know that this is a point. We know it asymptotes towards the x-axis, so we know that the function will do something like this, and then hit x equals 1. But we don't know if the function will do this, kind of like a 1 over x relationship almost, or if it will do this, something like that, where the curvature will change and actually it will bend down towards 1. We actually don't know right now. We can't distinguish between those two cases. So what do? Well, we need to look at the curvature function. So we need to actually look at the curvature of this bad boy, g double prime of t. And if you just rearrange this mess, then it's going to be equal to, well, you want to set, to make this a bit easier to differentiate, let's just make this look a bit different. So this will give you t. Now, if we bring one factor of a half, t to the half on the bottom, and shove it into there, then we get t to the minus 3 over 2, and we get a t in here. So this will give us, oh, I'd love a cup of tea right now, 1 minus t. Never get a British person thinking about tea too much. Jesus Christ. Right, anyway. Okay, so we've got minus a half, t to the minus 3 over 2, 1 minus t, and we're priming it with respect to t. This gives us 3 over 2, t to the minus 5 over 2, times 1 minus t to the minus a half. Minus, now this becomes a minus and a minus there, which cancelled, so we get minus a quarter t to the minus 3 over 2, 1 minus t to the minus 3 over 2. So let's just actually write that in. 1 over 4. Oh, that 2 should actually be a 4 because we've got half times a half there. Forgot that half boy from earlier. T to the minus 3 over 2, 1 minus t to the minus 3 over 2, right there. Okay, let's go ahead and try and solve this. And what are we actually looking for? Well, we're looking for a point where the curvature might change. The curvature might change, or will change, when there is a change of sign in this function. And there is a change of, we know that there will be a change of sign in this function if this function is 0 within our domain. So let's look for this being equal to 0. So let's just say bump, exclamation mark 0, 0, and then we can just sort of let's just factor this thing out. T to the minus 5 over 2, 1 minus t to the minus 3 over 2, times by 3 times 1 minus t minus t. I think that's correct. Is equal to 0 at some point where it changes. Let's just write this down too. And this thing can't equal 0 unless t tends to infinity, which is outside of our domain of t. So we're going to force this thing to be equal to 0. This thing is equal to 0 when t, well, we get 3 minus 4t here. And this thing is equal to 0 when t is 3 over 4. So, and when t is less than 3 over 4, then this thing is positive. When t is greater than 3 over 4, this thing is negative. So we can conclude that g double prime of t, i.e. the curvature, is something that's greater than 0 when t is between 0 and 3 over 4. It's equal to 0 when t is equal to 3 over 4, and it's less than 0 when t is greater than 3 over 4. But of course, t has to still be smaller than 1 in our domain. So pretty much, we know that we can actually now confidently sketch g of t So just bear with me whilst I rub this board clean. Okay, thanks for waiting and welcome back. We were halfway through sketching this thing, so we can now, with confidence, sketch this function. So now, with t on this axis and g on this axis, we know that g is 0 when t is equal to 1, and we know that it also asymptotes to infinity as t tends to 0. So we know that the function is going to be looking something like this. It will asymptote. We also concluded that the curvature changes sign at t is equal to 3/4. So we know, and remember, we knew that when t is less than 3/4, the curvature is positive, which it is doing here. Because if you think about it, if we kept going with this curvature, then the curvature will eventually go upwards. So that's what positive curvature is. And when t is greater than 3/4, the curvature is negative. So we know that it will start to bend down, doing something like this. Okay, so that's our g of t for the region of interest. Now we need to sketch this boy. Oh, okay, so how are we going to do this? Well, as I said earlier, this incomplete beta function is indeed the integral of g of t between 0 and x. What does it actually tell us? Well, it tells us, given a value of x, it will spit out the value of the integral from 0 of this function up to x. And that is simply the area of that function from 0 to x. So you can think of this incomplete beta function as just the area up to a point x beneath the g of t function, which we already know, and we already know how it looks like. Hence, this thing should now not be too difficult. The second way you can think about it is that, and from the derivative video, you can also conclude this, that the derivative of this incomplete beta function is going to be equal to g of t on its own. So another way of thinking about it is that this g of t, this blue line, is just telling you what the gradient of this function is at each point. So it shouldn't be too difficult to sketch the incomplete beta function now. All right, so let's draw our axes. Nice big axes. So we have 0. Now we've got x here. This here will we've got our thingamabob, and this on this axis we have beta of 1/2 3/2 of x, which makes it an incomplete beta. Okay, well, when x is 0, quite clearly the integral, the area, is going to be 0. So we know that it's 0, 0. And we know that, okay, there are other convergence arguments. You could argue there are convergence problems with this. We actually can't say right now whether or not this integral will converge, because of course, arguably you do have an infinite area here. However, by comparison test, this integrand is always less than t to the minus 1/2, therefore, and since the integral of t to the minus 1/2 converges, therefore this integral will definitely converge. Hence, indeed, the area will be 0 when x is 0. Okay, now what does the gradient do? Well, the gradient is initially infinity. So initially it will be a straight line upwards, and then the gradient just continuously decreases until you get to 0, until you get to t equals 1, in which case the gradient will be 0. So the gradient continues to decrease until you hit x equal to 1, and at this point the gradient will be 0, i.e. The incomplete beta function will become a flat line, and this is our entire domain of interest. This is, remember that we are only going to be using the incomplete beta function for values of x between 0 and 1. So this is the sketch of our function over our required domain of between x from 0 to 1. So this is it. But there's still one piece of information missing. Here we've got beta 1/2 3/2 evaluated at 1, and well, we don't know what that is. Well, let's try and work it out. So beta, a half 3 over 2 of 1, is equal to, from here, t equals 0 to 1 dt, t to the minus a half, 1 minus t to the half. You can actually calculate the value of this integral using a trigonometric substitution. So you can use t is equal to sine squared theta. Why do I choose this? Well, we want something that will simplify this 1 minus t term to the power of a half. This will give something nice, trust me. Therefore, dt is equal to 2 sine theta cos theta times d theta. We can now shove this thing in. When t equals 0, theta is 0. When t equals 1, theta is pi over 2. So we get the integral from theta goes between 0 to pi by 2 of, now dt, we need to replace dt with that thing. So we get d theta of 2 sine theta cos theta. Now we have a t to the minus a half, so we get 1 over t to the power of a half, which is 1 over sine theta, so we get over sine theta. This beautifully cancels, and we get 1 minus t. Now 1 minus t is 1 minus sine squared theta, which is cos squared theta. We're taking it to the half power, which will give cos theta. So this will actually give us cos squared theta. Now, as we all know and love, 2 cos squared theta using the double angle formula will be, well, we know that cos 2 theta will be equal to 2 cos squared theta minus 1. So 2 cos squared theta is 1 plus cos 2 theta. And of course, you can integrate this yourself. Anyone who has a good know-how on calculus will know that if you integrate cos 2 theta between 0 and pi by 2, then you actually get as much above the x-axis as under the x-axis. So actually this integral is just 0. We already know it will be 0, leaving you with just the integral of 1 between 0 and pi by 2, giving you pi by 2. So we know that our function will, when x is 1, we know that this will be pi by 2. And that completes our sketch of the incomplete beta function. Thank you for watching.